Well, good morning. It's my pleasure to welcome you to Primetime in Bethel University Library. And Primetime is a series sponsored by the library to promote lifelong learning among students, faculty, administration, and community members. And today's presentation is part of the Edwin Scholars series. Edwin Scholars Awards was started a number of years ago by then Provost Barnes to recognize scholarship and collaborative scholarship between faculty and students. It's named after Edwin because in his founding vision for Bethel University in 1871, he actually talked a lot about what education at Bethel should look like and had 4 principles. And one of those principles was about the relationship between faculty and students. And he was committed to that relationship being a really collaborative one. So when Jay Barnes thought about trying to promote student and faculty collaboration in the summer and research, he came up with calling it the Edwin Scholars Award, which is a great name for it because this is about research collaboration between faculty and students. So this morning we get to hear from Dr. Adam Johnson in the psychology department and David Collins, who's a senior psych major, and they're going to talk about decision making in the brain, algorithms, and personality. I also want to announce that on Thursday the session will be with Pamela Irwin and her students who went to Ireland over interim, and they'll be presenting, I think this is a great topic, a great title, reconciliation. You keep using that word, I don't think it means what you think it means. So I hope you'll join us on Thursday for that session as well. So we look forward to what you have to tell us.
Well, good morning, everybody. Thanks for coming. So I'd like to begin just by pointing out that, so David, me, and then there's a third name up there, James Ash, who is a neurologist at the University of Minnesota, and he's been our collaborator through this entire project. And he is he has provided us with much of the data that we'll wind up showing you toward the end of it. And basically what we've been trying to do is figure out ways that we can really more deeply understand what's going on in the brain as people make decisions. So, all right, so just to point out to the first slide, heroin is bad, but why? This is actually a really salient question. And the answer, of course, is going to be, well, if I start taking heroin, you know, it may feel good at the time, but I may wind up having worse opportunities in the future. And so the question is, how do we actually make those decisions across time? So let me give you a brief sketch of where we're going. So the first thing that we want to do is we want to ask a really simple question of reward. How do you evaluate reward across time? And then what we'll do is we'll provide an answer for machine learning, and we'll break this into 3 parts. We'll generally talk about reinforcement learning algorithms for machine learning. This is more of the computer science, math end of the spectrum. And then we'll look at a few parameters that wind up being really, really important. And what's interesting about these parameters is they really dictate something about choice for these algorithms, and they map onto much of, I guess, the way that we look at personalities. And if we call someone impulsive, we're essentially saying something about the way that they make choices. And so can we find some correspondence between these algorithms and the parameters that exist within them and personalities? And so we'll try to make an argument that, lo and behold, yes, we can assess something about personality by having people play really simple games and giving them really simple decision tasks. So then we'll get into some of the brain issues associated with it. Then once we've established sort of what is going on from the machine learning side, we'll make an argument that these algorithms are actually what are used in the brain. And so if they're used in the brain, what we can do is we can estimate the parameters from a person's behavior to start to make an estimate of what personality type they are. And we'll tell you a little bit about how we estimate those parameters for a single subject. And then finally, we'll come back to brain activity associated with decision making and some work that we've been a part of where we can see different aspects of the decision-making process correlate with activity in different brain areas. And finally, we'll talk a little bit about future work. And this is an ongoing project that we've been on for about a year now, and there's still a year at least left. So this is a very big project, so we'll tell you some of those future directions. All right, let me take it away.
All right, I'm going to start with a very practical example so you guys can get a better idea of just what it is exactly we were looking at. And so I'd like to provide the stereotypical example of a college student. And so the 2 days I want to look at in particular are the 5 days before and the day before. And so the important thing to keep in mind here is that the college student has a decision he has to make. And the first decision is going to ultimately affect the other decisions that he has available to him. And so the first option you have that's available to you is, do I study in advance for the exam, or do I go outside and play Ultimate Frisbee? Because it's almost springtime, it's almost summertime, it's a beautiful day, or should I go and just study and work hard and get that A that I want? And so based off of their first decision, it strongly dictates what's going to happen next. And so you can see if you went the study route, what winds up happening is you have the choice of, do I put it off and study the night before and just cram it all in? Or do I form a study group and take my time and walk through the problems, go through the notes, and work hard? Whereas on the other end of the spectrum, if you played the Ultimate Frisbee route, you have the option of Xbox or pulling an all-nighter and just mainlining caffeine. And so ultimately you can see that each individual choice that you make affects the outcome of your test. And so if you went and worked hard and studied the whole time, you wind up getting an A. If you studied hard the first day and then put it off until the night before, you got a B+. And if you decide to play Ultimate followed by Xbox, you got a D. And then Ultimate Frisbee and caffeine, you got a C+. So this is kind of the direction we're going, so you guys get a better idea just what it is exactly we're trying to look at from our research this summer and ultimately up until now. All right, so the basic task that I spent a lot of time working on during the summer was programming using MATLABs to help or try to see what a computer would do given a certain scenario with rewards. And so as you can see, there are pathways that go along in that your first action ultimately dictates what your next actions will be. And so you can, if you look at this particular example, you can see that if you start out by going with the lower reward, you wind up getting a bigger option in the long run. Whereas if you go with the short-term reward and you want it right away, you're going to wind up getting a lot lower values. And so really it's a matter of which one of these is going to benefit me more.
So we can ask the question, if we start here at this position, well, if we do sort of the low payoff action first, then we've got access to higher payouts in the end. And so we have to, well, go away from something that's only moderately rewarding. So this seems like the worst choice if we're just considering the first action. So how do we actually manage to look beyond this first outcome to actually the overall outcomes?
Okay, and so as Adam mentioned, there's an optimal choice that you can make that's available to you. And so if you stick along the top pathway and go with 0.3 and then up to 1, your total reward is going to come out to be 1.3. And that's the big reward that you can look at. Whereas on the other hand, if you went the opposite direction, it's not nearly as beneficial. And so the big question becomes, how are we going to program something that it thinks all the way through the task or tries to factor in all the variables that are available to it? And so, as I mentioned, what happens if you can't think all the way through your decisions? And so, as Adam mentioned, you see that there is a value of 0.3 versus a value of 0.6. And if you can't look ahead, you can get the idea that the averages are about the same in terms of the values. You see 0.9 for the top two choices and 0.9 for the bottom two. So ultimately, if you didn't think ahead, you'd probably go with the bottom choice because the 0.6 is going to be the greater and better option for the agent in this case. And so that's what you can see right there.
So in order to actually make an optimal decision, you need to be able to think through multiple levels of choice. So if you've got a sequence of choices, your first choice influences your second choice. In order to make the best choice, you can't just, well, say, I'm just going to average together all of the possibilities that come afterward. But you have this struggle, and this is something that we all are faced with in terms of how far do I think ahead? So when you sit down, or I guess when you go to the DC and you're provided with all of these different options, do you evaluate how this meal, this immediate choice that you've got right in front of you, is going to affect, how it'll affect your sleep patterns, how it'll affect your mood, how it'll affect your weight, do we really play all of that stuff through? At a certain point, you just have to say, okay, that's enough. I need to actually choose something right now because the person behind me is getting kind of annoyed, right? And so there's this balance that we have to strike with thinking through things multiple choices ahead, but we also need to, so that we can look beyond the small immediate payoff toward a large long-term payoff, but we also need to be able to represent the consequences. And in those consequences, we want to be sure that we represent the most important aspect of the reward, as opposed to just sort of blurring things together and saying, oh, that's good. Now, in some cases, we have to do that. And we won't get into it. We've structured our task in such a way that you can actually think all the way through. But what you effectively have to do is you have to overcome this initial case where I don't want that immediate small reward. I want the immediate big reward. You have to somehow overcome that. So now this is the case that we have. This is the test that we have. And so now we'll go into the reinforcement learning side of it so that we can start to understand how an algorithmic approach can solve this problem.
Okay, so like Dr. Johnson mentioned, we looked particularly at reinforcement learning algorithms, which have a pretty simple goal. It's just simply the idea that we're trying to maximize the amount of reward possible for the agent. And so the first equation that you see right here is a simple rewards equation where gamma is simply a parameter where you can discount, thank you, or you can discount the future rewards and you try to weigh what the best options are available to you. And then you see R sub t, which is the reward at that particular time. And ultimately, tau represents any time in the near future. Is there anything else you want to add to that?
Okay, so we're summing up all future rewards. Does this make sense? So we've got sigma and we've got R. These are going to be all of the rewards that we have at each time step. And what we want to do is we want to maximize the total amount of future reward that we can get. Now, what gamma does is it's a parameter that basically says, you know, something that happens in 20 years. So if I were to ask you about this, give you this choice. Do you want $20 now, or can I give you $20 in 10 years? Which one would you select? I'll take the 20 now, right? And so basically that's what gamma captures, is the fact that out in the future, yes, it may be the same reward, it's just not worth as much. Does that make sense to everybody? So we've got that embedded within the equation. So we want to maximize all future reward.
So in order to maximize these future rewards, we look for what's called a policy. And basically what the policy is trying to do is trying to best identify which given state is going to give that person a maximal reward. And so, as you can see in the particular equation right here, pi represents the policy, and the s represents the state, and a represents the action. So the policy of a given state is going to provide you with the action that you need to get that maximum reward. And so we construct the policy based on the equation below that, where Q represents the value of a certain decision or a certain action, given the policy at a particular state and an action provides you the expected reward at a given state, given a certain action, and the policy that is available to the agent at that time.
So this is a little bit math. We're trending toward a little bit heavier math, but effectively what this equation says is how good is taking this action in the long term. And so that's what we want to be able to do. We want to be able to learn how good taking an action is, not just with respect to the immediate payoff, but with respect to all of the long-term payoff. And so we'll try to figure out how to construct, how to figure out the values, and once we have the values of the actions that we'll take, then we can very easily say, well, if this is the state that I'm in, I'm 5 days out in front of a test, what is the best thing to do? That's a policy.
Okay, and so the next step involved is looking at just what, using our example that we referred to earlier, what is the optimal policy for the agent in this particular scenario? And so as you can see, you have the starting point at or what we call state 0, and then the first two states that are available to it are the values of 0.3 and 0.6, and then it progresses onward. And so in order, in a particular example for our optimal policy equation that we just mentioned, what the agent is going to try to do is identify which of these gives me the maximal amount of reward in the long run. And so if we jump to the next slide here, you can see that after it had taken the action towards the top, it changed the value of this one right here to 1.3 because that's the optimal amount of reward it can receive in that particular situation. And if you look at the bottom now, that changed to a 1. So originally that was a value of 0.6, and then it took the optimal value below that of 0.4, so then that's why that value changes to 1. So it's summing up the rewards as it goes through the process.
So once we've sorted out these values, it's very easy to say, oh, well, this is the more valuable action, even though I'm getting less reward there. Make sense to everybody?
Okay, so the big question becomes, how do we learn and how are we going to model it? And so what we wound up doing is we tried to estimate state action values. And so as you saw in the previous equation earlier, it's a matter of having a Q value given a certain state and a certain actions that are available to the agent at that time. And so the way this works is that as the agent progresses through the task again and again and again, it updates the state action values as it goes. And so in the equation below, this is a very simplified equation so you guys can get a feel for what's going on here. you can see that it starts with the old estimate, which is the original value that it has, what it knows about that particular situation. And then it also factors in a learning rate parameter, which we'll discuss here in a little bit. And then the prediction error. And based off of the value that you get from those last two variables, we'll adjust it or update the estimate to a new value, which will probably be closer to what the actual value will be.
So effectively what we can now do is we can get into a situation, let's say, you see that at the fountain drinks dispenser, there's a new flavor of soda, and you think, well, what's the value of that? I have no idea, right? So it may be terrible, it might be good. And so what you can do is you can fill up your glass, you can take a sip of it, and you can discover, this was fantastic. I did not expect it. It's a prediction error. So my experience deviated or diverged from what I predicted. So now what I can do is I can learn something about the value of that new type of soda, and I'll update that estimate. And so the next time I can come back and I say, oh, that's a very good soda, I'll take it. Or we could go the other direction with it. So.
Okay, so here's the big, ugly, nasty equation that we wound up using. And the approach that we took is called QLearning. And so basically this is an algorithm that looks specifically at state action values, as I mentioned on the last slide. And so what you can see here is this is pretty much the same equation, except for one thing. So I'm going to jump back quick. So you can see that there's the old estimate plus the alpha times the prediction error. And so that big bracketed region, that's the prediction error. So that gives you an idea of just where exactly we were heading in this. And Dr. Johnson will explain that a little further on the next slide. But the key point you need to look at here is that there are key parameters involved that dictate the behavior of the agent. And so in this case, there's what's known as a learning rate and a discount factor, which we'll also explain later on here. And the other key thing that I want to talk about very briefly is the idea of model-free learning. So essentially what this is saying is that we don't need to compute, we can't compute more than one step at a time. And so basically, if you think about it like this, if in a case of a model learning task, you're going to have a map available to you. So you can easily identify where something is or how to get to that point and what the values are. In this particular case, the agent has no idea what else is out there. So it has to explore and try to figure out what else is available to it, what's the best options that it can take.
One of the big differences between model-based learning and model-free learning is that model-free learning is going to allow you to make that decision really, really quickly. So you know when there's that person behind you at the soda line, and they're really grumpy, and they're sort of making those, get on with it already. And you can't think through, oh, how is this going to affect me? You can't think through all of those possibilities. You just need to make a choice. That's model-free learning. If you can sit there and daydream for a while and go through all of the ramifications of this choice, that's going to be something much more related to model-based learning, because you've got a model of how things are going to work out. So at this point, we're trying to figure out how people make those really fast choices and how they learn the Q values for those different choices. All right. Okay, so now we've got our prediction error. So the big issue here is how do we actually compute what a prediction error is? How do we identify that divergence between what we experience and what we expect? So we're going to have what we expect. This is our old value of Q. So we went up to the soda machine, we expected, hey, this is going to be pretty good. Pushed the button, got it, and had that experience. Now, the issue here is that we're going to have the reward that we received from the situation, but also this other piece, which is, this is how much reward can I expect to get in the future. So maybe I got a big reward, but it puts me in a position where I can't expect anything good in the future. So that's going to be the expected reward will be a combination of these two. Now we've got this discounting factor again, and this is going to be the way that, remember I said $20 in, was it 20 years, something like that? You didn't want that? That's that discount factor coming up again. And so basically, we can discount the future. Yeah, sure, I get a bigger reward in the future, but I don't really care. Comes into the way that we predict this, the way that we can have a prediction error. So basically what happens is, if our prediction error, or delta, is 0, then we've exactly gauged our expectations appropriately. And when we experience something, we go, oh yeah, that's exactly what I expected. I'm not going to change my behavior as a result of this experience, because it was either good or it was bad, and I knew that. Now, if I have a positive prediction error, basically what it means is it was better than expected. If I have a negative, prediction error, it was worse than I expected. And this is actually a term that winds up coming up in particularly areas of addiction, that certain drugs tap into these sorts of signals and basically tell you it was better than you expected. And so you wind up learning every time that you take the drug that things are always better than you expect. Does that make sense? It's a little bit of a strange idea. But this is the prediction error, and this actually has a physiological correlate in the brain. So, all right. So before we get there, what we have to do is we have to show, we want to make sure that you understand. We've got our 4-choice task that was, and we started off, and we can get any values that are summed rewards that range from anywhere from 0.8 to 1.3. And so if we're going to show you that the algorithm works, the average reward across those 2 choices should increase. And what you can see is that at trial number 0, the algorithm doesn't know anything. And as this is going to be average, a filtered average of the reward, but you can see that across experience, the algorithm starts choosing the optimal action far more than it chooses the non-optimal actions. And so we can actually use this algorithm in order to uncover or learn what the optimal policy is in this case. And by policy, remember, I'm just talking about the best set of actions.
Okay, so here's a cool biological implication of what exactly prediction error is. And so in a study done by Schultstein and Montague in 1997, they took monkeys and tapped into the dopamine centers of their brain. And so what dopamine essentially is a neurotransmitter that one of the implications that it has is that you get excited when you get a reward. So it's like, yay, I got something! You get all excited, there's that flood of endorphins and all that excitement that you get for getting something. And so what they wound up doing is that they took the monkey and initially with no expectation of a reward coming, and they gave it a reward. And as you can see right at the reward spot, where the R is labeled, you can see there's a spike in dopamine.
So these are going to be the times of spiking from dopamine neurons, and you can see that there's a little bit higher density region immediately after the reward. So monkey suddenly gets a bit of juice. Oh, that was really nice. I didn't expect that. There's this surge in dopamine.
Okay, and so on the next graph you can see that in this case the monkey is anticipating a reward and the reward actually happens. And so you can see at the conditioned stimulus the spike happens right away. And then as it gets towards the reward it just kind of levels out, and then in comparison with the reward predicted and no reward actually happens, there's that spike again right away at the conditioned stimulus, but then you can see right about 1.5 seconds there's this drop, just kind of this, oh, I didn't get anything.
So can you see the prediction errors here? Here we have, we just explained the algorithmic side of it, and this work has all actually come out of the algorithm side, that, oh, we couldn't make sense of what's going on with these dopamine signals, and then some machine learning, computer science people said, you know, I've seen that before, why don't you check this out? And so we run this test, and basically this is going to be that prediction error. We wind up saying, oh, you know, I don't really expect that I'm going to get any reward. As soon as that stimulus that says you're going to get reward comes on, whoa, good. I didn't expect that to happen, and so I get this little surge, and then when the reward actually comes, then it's just sort of, yep, that's what I expected. It's not any better or any worse than what I expected because I had an appropriate expectation. So we've now, I hope that what we've done is we've managed to take you from here's an algorithm, now we can get over into the actual physiological substrates of it. Okay, so now for this discount rate. This discount rate is critical because what it does is it actually dictates what these values are. And so what we can do is we can say, okay, if this is what the return is, we can go through these calculations and we can say, okay, if I'm discounting future, well, I've got 0.9, I'm going to raise it to the second power because my discount rate is 0.9, and because this is 2 steps away. And so how valuable this actually is 0.81, even though I'm getting 1 unit of reward. And you see that we're raising 0.9 to the first power here, and so actually this is diminished but just a little bit because it's closer in time. Now, if we do the same thing to the other side, it winds up that I've got a total reward that's still bigger along this path on this direction. So I'll still take this if I have a 0.9 discounting rate. But if we wind up having the discount rate being as 0.2, what happens is it turns out that I massively discount this reward that's further out in time So much so that, it's not really valuable anymore. And this is the best way, the best set of actions to take. Okay, so now let's move on to the next parameter. So what we can do is we can look at the way that people, or our algorithm, choose the more valuable long run versus the short run. And what we see is that if we have gamma levels set very low, most of the time we're choosing the state 2 action, which gets us the sort of immediate reward, but not long-term reward. And as we turn up gamma to 1, we switch and we start doing what the optimal action would be. Okay, so then we have got the learning rate or behavioral stability. This parameter actually is going to correspond with, if you've got a prediction error, what do you do with it? So imagine you go to your soda machine, you get that little bit of soda, and it's terrible, right? You thought it would be really good. So do you say, this is terrible, I'm never doing it again, right? You take that prediction error and you immediately change the value of it so that you never do it again. That would be having an alpha level that was very high. And so this is going to make it so that you learn very quickly, but it also has the problem that it's very unstable. So any prediction error that you have, you completely change your behavior. Does that make sense? Now, if we have alpha set to low values, then what happens is, I got that soda, it was bad. I don't think I'm going to choose it so frequently, but I'm going to give it another chance. I'll choose it again. Does that make sense to everybody? So we'll learn more slowly, but we've got much more stable behavior. All right, and our last parameter is beta.
So the last parameter is an inverse temperature parameter, or beta. And so what beta is basically describing is how much of a difference in value between different options matter. And so if you look at the far left, there are 2 actions available, each having different amounts of reward. And so the action on the far left has a value of about 0.7, whereas the value on the right has a value of about 0.3. And so as you can see on the far right, as you increase beta, the exploration decreases. And what I mean by exploration is that when beta is set really low, the agent essentially is going to say to itself, okay, I really don't care what the best option is. I'm going to look around and keep exploring, trying to find what is available to me. And as we increase the beta, the agent starts to say, okay, well, there are probably other options available, but I like this one, so I'm going to stick with this one. And so as beta keeps increasing, it's going to get more and more focused on the most valuable value available to it. And so if you look over here, you can see just the change in fluctuation in, as you increase the beta, action 1 becomes more popular. And as you increase the beta for action 2, it plummets downward. And so the interesting thing is, though, once you set beta too high, and if I say throw in a third action right now, it would probably completely ignore the third action because it's set on that first action already. It won't even bother to explore and see that there's a new one available to it.
All right. So what we actually hypothesize is that you can use these 3 parameters. We've got gamma, we've got alpha, and we've got beta. These all correspond to specific aspects of a learning algorithm, but they wind up being quite useful in describing someone's personality as they approach decision processes. We know people who don't really care about the future. Oh yeah, it's in 5 minutes, I don't care. Or we know other people who say, okay, I've got this choice, I'm going to think through things, okay? And you know what, the future really doesn't matter, I'm going to do this. And so that's going to be a difference in discount factor, and it corresponds in personality to differences in impulsivity. We've got learning rate, and so I just got a prediction error, what do I do with it? How reactive am I? So, oh, this ruins everything. We all know people who throw their hands up, and we wind up, they are always apologizing, right? Oh, I'm sorry I was that way. It wasn't really that big of a deal. But does that make sense? That basically they're changing the value, and I'll never do that again. Oh, now I'll do it all the time. Now I'll never do it again. And so that would be a really high alpha. And we know some other people who are very stable, and you know what? That was a bad situation. Happened once. I'm going to come back. And so in terms of decision making, this alpha parameter seems to correspond to some of that stability or reactivity in terms of personality. Finally, we've got this inverse temperature parameter, beta, and this seems to correspond with exploration. I know what's good. I'm never going away from what's good. Or actually, on the flip side of it, sort of, you know what? I've got one thing is more valuable than another thing. I don't really care. Are you the type of person that, if you go down to the shop, the bookstore, and you're getting a soda, If you've got one soda that's 65 cents and you've got another soda that's 55 cents, will you always get the one that's 55 cents? Because it's cheaper, right? So we know people like that, and that's actually what this beta parameter actually manages to get at. All right, these are coarse aspects of decision making, and we'd like to make dig into these a little bit more. There's lots of computer science work that's been done on how we can basically understand these factors and break them down further. But for our first pass, this is sort of a new and developing field that we're trying to take these parameters and look at them as parameters for you, me, and the next person. So, all right.
One of the cool things we did with this too is that we actually would adjust beta over a period of time too. So basically it started to reflect human behavior a little more, because you start out exploring your options and seeing what's available to you. But over time we'd adjust the beta so it was higher, and so once the beta was adjusted, it would start to stick with the path that it knew was best at all times. And I thought that was a neat addition once you start, and that's what it means by coarse aspects, that you can really start to vary things up a little bit, and you can start to describe human behavior a little better versus just keeping the parameters constant through all the tasks.
All right, so with our time constraints, we didn't know if we'd be able to get this part of the talk in. This is some nasty math that we've been working through, but this is parameter inference. And basically, what we want to do is we want to use someone's behavior. So we give people this task and just have them play it over and over again. Okay, run through this task 300 or 400 times. Let's see what your behavior looks like. And we'll use that behavior to try to estimate this alpha, beta, and gamma parameters. And so we used what's called Bayesian inference for this process. And I think basically what I'll say is that what you can do is you can run a computer algorithm thousands of times and come up with, okay, if I set the parameters exactly this way, what type of behavior do I get? And then you can take someone and you can look at the way that they behaved, and you can say, oh, their behavior looks incredibly close to the way that the algorithm ran when I had the parameter set in exactly this way. And because of that, I can make estimates of those parameters and what the parameters alpha, beta, and gamma would be for Dr. Nevins, Dr. Boyd, Dr. Hopkins. Make sense to everybody? So that's a lot of stats. It's a lot of other stuff that I won't bother going into, so let's just skip these slides. Okay, so keep on going.
Okay.
Yeah.
Okay, so back to the original task at hand, just to kind of get into the brain scan portion of things. This is what we set up again in the beginning of the summer, and trying to really see how a computer program would go about solving the problem and trying to identify what the best values are available to it. And so, as you can see, and like what we talked about, the immediate, like, I want it now kind of idea, or getting the 0.6 value, results in you getting a much lower overall or total utility value of reward. Whereas on the other hand, if you take the long-term route, you wind up getting a much higher reward as a result. And so what Dr. Ash wound up doing is playing with brains.
So basically we can give the test the same set of choices inside a scanner. And if different brain areas process information differently, what we should see is that for some aspects of the task, we'll have one brain area that works a whole lot harder than for a different aspect of the task. And so if you were to say, think about the future, well, that's going to activate some brain areas much more than others. So if you're thinking about the future, let's say if you're imagining what it would be like outside on a real spring day as opposed to what we've got today, you'd be activating areas of your brain like the hypothalamus, which is going to be related to temperature sensation and temperature regulation. You're also going to activate the hippocampus because you really need to dig into memory in order to understand what a real spring day looks like, right? So we would see a whole lot more activation. So now what we can do is we can say, okay, when people wind up going with the short term, that impulsive choice of just give me the 0.6 now, I don't want to wait for the 1.3 in the long run, we can look at what brain areas are most active. And we'll compare that to what brain areas are most active when the people chose, I'll hold out. I'll take the long run best action. And so what we see is that we get areas through, particularly this region. This is going to be frontal cortex, and there's a nose. So back of the head, front of the head, top, bottom. Just want to make sure everybody knows what we're talking about. This is a sagittal section. So what we see is that particularly through the anterior cingulate gyrus and the anterior most aspect of the anterior cingulate gyrus, we see activity that basically looks like, give it to me now. Right? I just want what I want. And so this seems to correspond with impulsive behavior. And when this brain area winds up being most active, people make impulsive choices. In contrast, we can look at the brain areas that are activated in the overall return when people wind up going against that impulsive action. And what we see is that there are more posterior aspects of the anterior cingulate gyrus. So the anterior cingulate goes around here, and what you can see is that as opposed to being really in the anterior section of it, we're actually back toward the middle section of the anterior cingulate. So, all right, on the next point.
Okay, and so a variation on the task, what Dr. Ash looked at as well was the idea of the incongruent or the conflict condition versus a congruent or a no conflict condition. And so like how we talked about earlier, how you set it up so that when you look at the initial point values, you try to determine which one's going to benefit me more in the long run. And so you can see in this case, there's a point value up top of 1.3, and there's a point value at the bottom of 1.0. So it really becomes a matter of which choices are going to benefit me the best in my current situation. So that's what he looked at in terms of the conflict task. And then in contrast, he had a congruent or a no conflict task where the short-term gain and the long-term gain are in the exact same pathway. So there was a lot less stress involved in trying to figure out which one's better for me, so they would fly through this one a lot quicker usually.
All right, so in this case, effectively what has to happen is the subject has to resolve this conflict. I want that right now, but this is going to be better in the long run. So how do I actually sift through that? And what we see is that we get a number of brain areas that are activated, but instead of just being down at this anterior cingulate level, we wind up getting these premotor areas, and an area of the brain called supplementary motor area, which is very much involved in sequential movements. And so now what we're seeing is that even in, this isn't a movement task, this is just I push a button, I push a button, and it's the same movement that these subjects are producing. But we see that the value computations and that resolution of the conflict actually corresponds to activity in this brain area. So this brain area seems to be very important in resolving that conflict. We know from other studies that people with damage to this brain area wind up not being able to resolve that conflict very well. So, all right, so to wrap up, we, for the modeling work, basically what we've done is we've said, okay, these parameters for reinforcement learning algorithms can be used to really describe the stable aspects of a person's decision-making behavior, and we can actually estimate these from individuals' behavior. So what we'd like to do in the future, and Dave and I have been talking about this, is actually going through and giving the classic psych battery personality inventories, and then going through and giving someone this type of, oh, just make some decisions and we'll see how the values work out and what choices you make. One of the advantages of this is, how many of you have taken a personality test? How many of you have read the question and go, I know what they're talking about, I'm going to write this? You guys have done this before? Okay, so now, how does someone do that when you just say, okay, you know what, I'm going to pay you some money for the rewards in this game? Just do the best you can. And you go through this, maybe we'll actually get a little bit more stable way of assessing personality, particularly within decision-making processes, and so you don't get this, oh yeah, I'm going to remember that I only do good things when we're talking about decision-making process. And so we're going to go after this problem in the future, we hope. Well, if Dave sticks around, if he doesn't, I'll have to recruit someone else who is as bright. And then the second piece of it is we're going to be doing more analysis and more specific individual analysis of the brain imaging data that we have. And so we'd like to be able to go through and see how different subjects can be scored in terms of these parameters, these decision-making parameters, and look at the way that their brain activities differ based on those parameters to see, is it really that this brain area is winding up winning out more often than not, and that's why these people are more impulsive than the next person. So, all right. Finally, we should acknowledge people that contribute to this. So James Ash is at the University of Minnesota and the Veterans Hospital. Paul Schrader is a collaborator of mine from the University of Minnesota, the Center for Cognitive Sciences, and he's helped a lot with the development of the algorithmic machine learning stuff. And then funding. The Edgren Scholarship, very much want to acknowledge that. But then as far as the data goes, these data cost a lot to collect. And so the Brain Sciences Center at the Veterans Hospital supported this, and the data came from a grant from the National Institute of Mental Health to Dr. Ash. So with that, any questions?
I noticed that there isn't any factor of risk, and I was wondering, because if you look at the values, it goes 3 and to either 1 or 0.2, and that if you had a 50% chance, that would have a greater risk than to go the higher reward in the short term.
So one of the things that Anthony is bringing up, and that's a really important point, is if I told you, okay, you get to repeatedly play this game. I'm going to give you the option. You can buy a lottery ticket for lottery 1, where 100% of the time you get $5. Or you can buy a lottery ticket for lottery 2, where 50% of the time you get $10. If you play this repetitively, what happens is you get exactly the same output, right? You win the same amount. But what happens both in humans and animals is they do this risk assessment. And if I were to ask you, can I get a show of hands, how many people would choose lottery 1, $5 for sure? How many people would choose lottery 2, $10, 50% of the time? Okay, we wind up, most humans are risk averse, and we'll say, just give me the sure thing. I don't care if it's less. And so at this point, we haven't incorporated that, but that's one of those further steps that we can go into how we should discount, and divide that discounting parameter up a little bit more. So we'd like to go there, we're not there yet.
How about you factor in perceptions of value?
Well, perceptions of value, this becomes a little bit more complicated. So Dave, can you bump it back to the diagram of the task? Okay, so in this case, the perception of value, so you can have this perception of where am I along this decision making? And sometimes people get a little bit confused and they think, oh, I'm here when I'm actually back here, and so they take the wrong choice. And then you can get into perceptions. If you get into how much is $1 worth to you, it's probably not worth as much as the person next to you. Those are some really difficult questions that, at this point, all we do is we basically say, I have no idea of how much it's intrinsically worth to you, but what I can say is, you and Deb respond differently when I offer $1. So I'll use that and I'll just say, hey, there's a difference in behavior.
How do you guys feel about MATLAB?
What?
How do you guys feel about MATLAB?
I feel great about it. Dave does most of the time. This is the programming language that
Thank
we
you for
use.
speaking for me on that one.
I definitely don't want to let you go too far down that road. Okay. Were there any more questions?
Well, I just wondered about the initial example where you had a student picking the results of a test.
Mm-hmm.
And then what I found myself thinking, and I don't know how it fits in the model, but what if they have different motivations? Or how about like a multitask? So for instance, the person chooses, what if they want to have a better relationship with their friends and they don't really care as much about, so would that just be a different task? Or is there a model that deals with a variety of motivations or tasks?
One of the things that's really quite interesting about this work, and it's only been about the last year that people have tried to make a correspondence between these parameters and the machine learning algorithms and personality characteristics, is that these parameters wind up really, doesn't matter what the decision is that you give. So what we could do is we could use this task, assess someone's parameters, and they wind up bringing into the next task. We could give the algorithm, we could give a person a completely different decision-making task. But because we know something about their parameters, we can assess how they'll learn on it. And we can actually predict, in some ways, what the best, learning strategies are going to be. What information should we provide them? How should we motivate them? And so it does wind up getting to some of those questions. And they wind up, it's a little bit of a departure from what you're asking is how are people motivated, to, well, there are some basic aspects of the way that we make decisions, and then we have to figure out how the motivations tap into those basic ways of making decisions. So that would be a long way down the road. We have gone over. Thank you for your time.